All right, well, welcome back to E76. So I'll be with us for most of the remainder of the semester. Dan will come back at the very end when we'll tie everything together, as well as for the app party. So tonight we dive into the iOS half of the class, and with it, all sorts of new fun issues, new IDE in the form of Xcode. Pointers are back if unfamiliar, or if familiar, and you enjoyed that Java did not have them. And so the objectives today are to, one, give a sense of where we're going for the remainder of the iOS portion of the semester. Two, what resources exist to help you wrap your minds around this particular part of the course. And three, to introduce some material that we'll have to very quickly start taking for granted, namely the language of C, and also we'll introduce Objective-C, which syntactically is a little bit mind-bending, at least for some, it was for me. And then next week we'll transition to some of the more user-friendly WYSIWYG aspects of Xcode, actually implementing GUI-based applications. So without further ado, what help exists? So this is one of the books that's recommended in the course's syllabus, and I actually love this one. There's a whole bunch of iOS books out there. Realize that they're of varying quality, but also varying up-to-datedness. So iOS, the SDK that Apple provides for these devices, was updated very recently and very much updated last summer from 4 to version 5. And among the most important changes is how iOS handles memory management, allocating objects, freeing objects. In short, it's gotten a whole lot simpler than this time last year. So just beware picking up any book or online reference that uses iOS 4 or Objective-C 1.0. In short, I would err on the side of picking one of the recommended books if you are the type who learns well from references. What's particularly nice about this, as it says, it's actually in full color, which actually just makes it pleasurable to read. And it's also very nice and up-to-date and accessible. And a second book that's also very popular is this one here. We have linked on the course's website the source code that's freely available for both of these books. So even if you don't want to buy or borrow from the library a book like this, realize that the source code examples are at least online, so you can infer perhaps how to implement various features using those tricks. All right, so this is a command line, and it turns out that everything we do today could be done at a command line, but we will introduce this IDE known as Xcode, which is Apple's answer to Eclipse and Visual Studio and the like. Xcode these days has the option to use an old school compiler called GCC, G++, with which some of you might be very familiar, and also a newer project called LLVM, and with it Clang. And with LLVM and Clang, do you get a whole bunch more features, among them static analysis of code, which is just a fancy way of saying the IDE can catch potential errors in your code and provide nice little user-friendly yellow triangles, red triangles, saying this is a warning or an error that are more informative than GCC traditionally was. And it's become Apple's compiler of choice. And all of these details, though, are largely abstracted away for you once you install Xcode and start using it. So realize this is just some of the backstory for this tool. The tool that we will use is indeed Xcode. And here's the fine print for this course and really Apple development in general. Apple does not make it that easy to code on their platform unless you buy what they recommend and keep it up to date in a manner they specify. So what does this mean for us? So per the course catalog and the course's syllabus, you will need from this point forward for the course's 3 iOS projects a Mac, an Intel-based Mac that is running Lion, although there is a slight exception to that, version 10.7.3. Which is the latest as of today, and you will need to then download for free Xcode 4.3.1, which is available in the app that was added to macOS a few months back called App Store, and you can download it from an interface that looks a little something like this. You do not need to pay for Xcode. You do need to pay for Lion if you don't already have it, $29.99, but there are alternatives here. So if you're using a work laptop or home laptop that still has Snow Leopard on it and you really, really, really don't want to or can't upgrade just now, realize that you can download the latest version of Xcode for Snow Leopard if you pay a $99 fee to enter into the Apple iOS developer program. So you will see on the iOS setup PDF, the next project that's been released and is posted on the course's website, links to all the relevant information, a longer explanation of what this all means. But in short, if you have Line and you're up to date, you're good to go as early as right now or this evening. But there's some fine print to be aware of. Any questions on what you'll need in terms of hardware and such? All right. OK, good. So let's just paint a picture and then dive into some actual examples. So when we fire up Xcode, at first it can be a little overwhelming, even though Apple has increasingly tried to simplify things such that your IDE now looks a bit like iTunes, such that in the top left-hand corner, when you want to run your application, you're literally going to click a play button, and when you want to stop running it, you will click the stop button. But that really is simplified only in that they hid a lot of the otherwise complex functionality and fancy features under menus that are simply hidden by default. But just to orient us here with a little snippet from Apple's own documentation, it's actually structured very similar to Xcode, where on the left-hand side, generally you'll see the files that pertain to some project. In the middle, you'll actually see the code that you're working on. A nice view in Xcode is that you'll be able to split it, so you can see two files at once, whether for version control features, so you can see two things side by side. When we get to GUI development, so that you can actually see code next to the relevant UI and vice versa. In the bottom area, you'll see things like the debugging information, diagnostic output that you might have, a little console window that you can type in to execute GCC or GDB or LLVM commands. And then on the right-hand side is where they hid everything that used to make Xcode look all the more complicated. So you'll find sometimes that things are not visible by default because they've been hidden, but I'll try to point out in the PDFs and also in class where stuff is. And if this world is new to you, namely Objective-C and macOS development, just realize that there's typically very little harm in just futzing around, playing around, make sure to save things, but when in doubt, just poke around. Don't get overwhelmed by the hundreds of features that odds are you will never need to use, at least for the next few months. So here is the place to go to for informational content. So Apple actually has a very non-trivial amount of documentation online, non-trivial amount of sample code online. Personally, I find it rather hard to navigate. Even the sample code tends to be more sophisticated than is ideal for first-time learners of Objective-C and iOS. It's rather overwhelmingly organized, such that you have huge lists of available tutorials and whatnot, but not really organized, from my perspective, in an educationally optimal way where you start here and then here and then here. You kind of have to know what you're looking for. So what we'll do in this PDFs and in class is try to guide you through this documentation. Indeed, the first project spec has a few URLs that we suggest you dive right into, and what you'll find typically is that Google is your friend, especially when looking up the documentation for some class. Finding it through Apple's website is sometimes non-obvious, so Google will typically lead you right there. So that's it for the setup of the logistics of diving in. Now we need to learn C. And out of curiosity, how many of you knew or learned C at some point in the past? Okay, so almost everyone. Now how many of you could sit down and write a C project now? Okay, so that's good. That's good, because it means we can have a conversation here. So what I'll try to do is fly through some of the mundane, boring stuff like for loops and conditions and all of this, which is almost identical syntactically to something like Java, but spend a little more time on the interesting conceptual matters, among them pointers, memory management, and the like, ideas that you'll want to and need to understand comfortably, because we're going to start taking that for granted at the end of today and also next week onward, since Objective-C is a proper superset of C, which means we have to know C and then start building onto it with new syntax and with new features. If at any point I'm talking too fast or assuming too much, please just interject and stop me. So quick warm-up exercise. This is the most boring, among the most boring programs you could write in C. Just to start teasing things apart and oiling any squeaky wheels, what does this line up here do in a C program? For those who recall. It's okay if you don't. Okay, it includes a header file. Okay, so what's in a header file is a text file that ends with .h, and what's typically in a header file? Someone else.
Function name specifications.
Okay, function name specifications. So the declarations of functions called function prototypes. So what's the signature of a function? What does it return? What's its name? What are its arguments? Semicolon. You might have things like type defs, which if you call with C is a way of declaring your own types, or at least making one type a synonym for another. You might have declarations of structs, which if there too it's a little hazy. A struct is like a class or an object, but that has no methods associated with it. It's just purely data. So those kinds of things that you might want multiple C files to have access to. So you would include a standard io.h file in this way. The angled brackets denote that it's on the system. It's in the default system directories itself, something like /user/local/include or similar. or slash user slash include in this case, or somewhere else. And the include effectively tells the compiler, or more specifically the compiler's preprocessor, to go open that file wherever it is on the system and literally copy and paste its contents here and then proceed to compile the file. So it's replaced with the actual contents. All right, so this is just a return value. By default, this is one of the possible signatures for main. At least it's the one that Apple uses by default for all of their programs. Indeed, what you'll see in the iOS applications we write, they all start with something a little like this. The body does not say hello world. It has a little more interesting code within it, but all of our iOS applications will still have a main function like any C function, but that will hand control off to more sophisticated APIs that now exist on top of this. So argc is the argument count, the number of things you type at the command line, much like argc or argc or argv in Java. And same deal here. Const char star, though, gets interesting. So const is easy. It means constant. It means the pointer should not be changed. But what the heck is a pointer? It's an address. Okay, so Java doesn't have pointers. It has references, which you can still think of as addresses, but there's a layer of indirection there, whereby simply knowing the reference of a Java object does not mean you can go directly to that location in RAM. In fact, it's effectively a hash value that hides the true address in RAM from you, so that in a Java program you can't go touching arbitrary memory. And this is a huge advantage for security, because it means that you can't, with an invalid or deliberately with a pointer, start looking around memory, looking for passwords that might be hanging around somewhere in memory. It also decreases the probability of programming mistakes, because you can't dereference bogus pointers. A reference typically points to something that's valid, at least with higher probability. So in Java, you're protected against a lot of this. In C, and in soon Objective-C, we can start making mistakes, unfortunately. So char star means that this is a pointer to a character, and the casual description of this is a string. So char star means string, but why? And this room is not quite set up to let people draw and project, so maybe I'll draw this at the same. I'll draw it twice if need be. Let me draw this. Let's call this, I'll give this a name in just a moment. Okay, call that S. Then for those of you over here, there's got to be a better way to do this. Okay, so I'll stand here, but it's the same picture. So what are we referring to here? If I wrote a line of code that looks like this, I'm going to have to run across the room once more time. Char star s gets quote unquote foo. Okay, next time we'll do this in advance on a slide. All right, and over here, char star s gets quote unquote foo. Okay, I'm here, so I'm going to stand here now. So if we have a line of code in C that declares a pointer called s, a variable called s, and its type is char star, that means it's a pointer to a char. What does that mean? It's the address of a character. So if we drew a picture of this, we could draw s as a chunk of memory. It happens to be 32 bits on a 32-bit machine, 64 bits on a more modern machine. So I'll draw it as a square. And inside of that square is a number, like 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5 means that the first character in this string is at byte number 1, 2, 3, 4, 5 in my 2 gigabytes of RAM. So it's an arbitrary number, just arbitrarily choosing a simple number like 1, 2, 3, 4, 5. So we can draw this typically with an arrow, but if I really wanted to be anal, I could draw in this square or that square for s, OX12345 to represent an actual number. So what is a string? A string, of course, is just a bunch of contiguous characters. In this case, the string I've declared is quote unquote foo in double quotes. That gets saved in the world of C as FOO followed by this special character, which is the 0 bytes, so represented as \0. So in other words, a pointer to a char is effectively equivalent to a string because the pointer gives you the address of the first character. And how do you figure out where the string ends? Since we don't have a pointer to the end character, it seems. The 0 bytes. You can infer, albeit inefficiently, but you can walk the string, is this 0, is this 0, is this 0, and finally when it is, aha, you found the end of the string. So this is the basic building block of a string in C. argv, meanwhile, though, has square brackets here, which means it's an array, of course, but the type of every element in that array is apparently what? Char star, so that simply means that argv is an array of pointers to strings. So if I were to redraw this, instead of having a single pointer, I would have an array of these pointers, each one of which might point to a different string. What strings? Whatever words I typed at the command line. If I ran a program called a.out, which is the common name in C, a.out space foo / bar / baz, all of those words would end up in memory like rectangles there, and the array would contain pointers to each of them. So that's all that's going on there. All right, any questions? That's pointers in like 5 minutes instead of an entire semester. All right, so we'll see further examples of this, but for now, just if it's hazy, just remember this kind of picture. A pointer is just an address, and it gives you direct access to locations in RAM. Java hides this kind of detail. So lastly, this is probably pretty familiar. Instead of having to write system.out.println or printf, we can instead just say printf, which is a function that's declared in that file. In other words, the signature for that function is in this file. Hello world is just a string, \n is new line, so this is just like Java. Return 0 is the convention for main, whereby you should return 0 if all is well, and any non-zero value if something went wrong. So that's it for hello world. So, okay, this part now we're going to start flying, since most of this stuff is just to make sure you realize we have a complete language here, but is otherwise old school. So statements we have in C, which look a little something like that. Variables can be declared just like Java here. Primitive data type. So we'll still have things like chars and doubles and floats and ints and longs. We have things like unsigned ints. We have things like long longs for 64-bit values and others. But for the most part, these are similar to what you've seen in Java. Printf. So this is something we'll see quite a bit, not so much with the printf function, which prints things to the screen, but we're going to start seeing soon in nslog, NSLOG, which is going to be a function in Apple's Foundation class, that their Foundation library. So a bunch of code they've written that uses these same format codes to print out things to Xcode's debugging console, or to iTunes, or to your own computer when you have the device connected with a USB cable. So %s, just to take the emphasis off of my voice, represents what? So a string. So it's a placeholder for a string. %d is decimal digit, so an int typically. LU, unsigned long, and then LLD is long int typically. F is a floating point value, a real number. And there's others, and we're going to see yet another in the context of Objective-C, but this would allow me to do something like this. In my printf statement, if I wanted a placeholder, I could actually do something like hello %s, comma s, where s then is declared to be char star s gets quote unquote David. David would be plugged into that string thanks to printf's substitution mechanism. All right, so that's it for variables and printfs and data types. Boolean expressions, we've got everything that we have in Java, so there's just a rattled off list. Conditions, we're going to see ifs and elses. Loops, we're going to see for loops, which look just like Java. We're going to see while loops, which just look like the same. We've got do while loops. So in short, there's really nothing new. Even if it's been years since you've coded in C, all of the syntax has pretty much been borrowed by more modern languages. So what about casting? What does it mean to cast one thing to another? Java certainly has this. Changing the data type. So you can go from one to the other, which can be in terms of primitives. You can cast a value like 3.14 to an, which is a double or float, and you can cast it to an int. And what happens there if you cast float to int? Yeah.
Truncates everything past 3.
Exactly. Just truncates everything after the trailing decimal point. So you just get an integer value of 3. It doesn't round. It effectively floors it down to the nearest int. And you might use this not in the context of primitives, but also in the context of object-oriented programming, where the only constraint is if you want to cast one object to another, what needs to be true about those two objects?
One has to be derived, like the right hand side has to be derived type, and the left hand side has to be the superclass.
Exactly. You have to have some kind of relationship between those two classes, some kind of hierarchical relationship whereby if you have a human class and then a male class and a female class that descend from that parent class, you could certainly cast a male object to a human object, but you couldn't necessarily go in the reverse direction because they might instead be a female object. So that's the idea behind casting, and it allows you then to inform the compiler that you know what you're doing. You want to make sure to treat subsequently this object as type male or as type human, depending on which direction the cast has gone in, so that it doesn't yell at you if you try calling methods that are distinctly male or distinctly female. or something like that. And so we don't typically have to do this, but you will see that there are some cases in the iOS world where it's quite commonly done so that we can pass around otherwise fairly generic pointers. So pointers can be pointing to anything. We've only talked thus far about char star, but you can certainly have pointers to a double, which means the address of some 64-bit value, most likely in memory. You can have pointers to floats, ints, longs, really anything. And pointers allow, what are pointers useful for? Beyond strings. If you just have a pointer to an int or a pointer to a long or a float or a double, what's the value of that? Passing by reference, exactly. So if you want to be able to mutate some value in memory, like an integer called n, you can't just pass n into some other function because you're just going to get a copy of those 32 or those 64 bits. You can change them, but it's not going to change it outside the scope of that function or method. So with a pointer, you can say, go to, here's the address of something I want you to change. If you then dereference that pointer, so to speak, you can go mutate whatever you want in memory. And therein lies the power, but also the danger of something like C. You can go wherever you want. All right, so a struct. Struct I kind of spoiled earlier, whereby we can store data inside of a struct. So here, let's actually take a look at an example, because this one starts to get a little more interesting in terms of capabilities. So I'm going to go ahead and open up among tonight's examples. And if you'd like to play along at home, all of this is online. And as an aside, for those unfamiliar, if I'm going a little too fast with regard to some of the basics of C, realize that among tonight's examples are a whole bunch of simple ones too. Examples for for loops, do while loops, and conditions. But I suspect it'd be fairly mind-numbing collectively to go through such detail. But realize we've put those examples together if you'd like to play around, just in case most folks are familiar with those things. So let's take a look at the struct example. So let me open up struct.xcode project. And just to orient us to the IDE, I've hidden most of the features here by default, but on the left-hand side, we see a list of all of the files in this project. There's very few. There's main.c, and there's a red file called struct. It's red because I haven't compiled the program, so that will be my binary, my executable, but right now I've not yet clicked the play or run button. And then here's my code, and then everything else, for the most part, has been hidden. So what's this program do? Well, first, let's scroll down to the bottom before looking in any detail at the struct, and we'll see this. In main, I have int argc, const char argv, and then below that, I'm apparently declaring a variable called Alice that's of type student. Suffice it to say, student is not some built-in struct or class or data type in C. I've declared it up top. Alice.age means go inside the Alice structs and assign the age value, the number 20. Alice's name should be quote-unquote Alice, and then I'm calling a function called greet and passing in Alice, and I'm doing the same kind of thing for Bob, but with slightly different values. All right, so up top, why did I declare this thing up here, greet, as a so-called prototype? What does it mean for there to be a function prototype? And once this goes away, we'll see it again. Why did I put that there, Dan?
Compiler goes top to bottom, so if it's not initialized, it won't bring it as the function.
Exactly. So C compilers and even Objective-C compilers are kind of dumb in that they only read things top to bottom. And so if it is reading this file top to bottom and it encounters this line here, greet Alice, or this line here, greet Bob, but you have not taught the compiler what it means to greet an argument in that way, the compiler is going to yell and it's going to say undefined symbol or something to that effect. But if I know I've implemented it just later in this file or in some other C file altogether, I can declare this prototype, which sometimes goes in a header file, .h file, but it can also go in a C file, that here, there is a function called greet. It's going to return nothing, so it's void. It's going to take in as an argument a student variable, and let's call it S, even though the S isn't even strictly necessary, semicolon. So that then tells the compiler, go on a leap of faith that this thing exists, and hopefully, toward the bottom of the file, indeed, there it is. So this function does very little, takes a student primitive as an argument, printf hello, comma, %s, there's our string placeholder. I see that you are something years old. And so syntactically, if I want to now plug in those values, as you might in Java, s.name and s.age. So no pointers here. This is just a structure. But as I said earlier, the downside of a C struct is what? There's no methods, or downside at least if you want those to be there. It's really just a container for data. And as an aside, you can simulate methods with things called function pointers, but things get fairly messy quickly if you try doing that, and thus were born other languages. So here, type def struct. Here's how we do this in C. And we're actually doing two things here at once. It's just a common paradigm. Type def is declaring a synonym of one type for another. But in this context, I'm declaring a type. It's a structural type. Inside of any such struct is going to be an int age, so that's probably 32 or 64 bits, and then a char star, so a single pointer to a name, and the name I want to give to this new data type that I just invented is student. So you'll not often have to declare your own structs or type defs in Objective-C, but what you will find in the iOS SDK is a whole lot of type defs that have happened, a whole bunch of declarations that Apple has made for you that you'll see throughout the documentation. It's just they've been implemented in Apple's own .h files. But any questions on structs? All right. What about enums? So what is an enum for those who recall? Enumerated values. And what is their value? What's their role typically in a program? Switch statement, you can use them in a switch statement because ultimately they are just numbers. And it's a very common way to declare constants without having to hard code values. So an alternative to using an enum would be to say sharp define, so the sharp symbol define, and then female space 1 to arbitrarily associate the number 1 with female, and then sharp define male 2. Now this is fine for a binary world like male and female, but if you have a list of 10 constants or 20, it just gets a little dangerous or a little tedious to maintain a list of this is number 1, this is number 2, number 3, and if just because you're a little anal you like to alphabetize things, that's bad, because if you now change these values and those values have been saved elsewhere on disk or in databases, bad things happen. So enum at least allows you, although enums don't solve that latter problem per se, but enums allow you to at least get out of the business of having to choose these numbers for yourself. So they will essentially, this enum will assign to quote unquote female in all caps the number 0 by default, and male will get the number 1. But more compellingly, I've now said that male and female are instances of a brand new type that I just invented that I've decided to call genders. So now I can declare variables of type genders and then assign them values of male or female. So I've invented, so to speak, another type. At the end of the day, it's still just a number, but at least I didn't have to arbitrarily hard code numbers with these things. So these two are incredibly common in iOS. You'll find that the names given to enums are much longer than genders, but this is a common paradigm. But notice what I can now do. If I want to mix now these two features of the language, I can now associate with, say, a student, his or her gender as well. So I've jettisoned the age in this example. I've just kept the name, but now I've said that genders can be a field in the struct as well. So something we'll see commonly. Yeah? Why don't we use pointers with these type defs? Good question. Short of it is it's not necessary for the following reason. A gender here is simply a value, and it's going to be underneath the hood 0 or 1. It's effectively a primitive. Name has to be a pointer because the way to implement strings in C is by way of the discussion we had at the board. So by contrast, if I did reintroduce age, recall that age does not require a pointer. I can simply say int age. The problem is, if I instead did this, I will be telling the compiler, give me space for the address for an address of an int, call it age, but that's not going to give me space for what? The age itself. So I could still mitigate that problem by using a function in C called malloc, and I could dynamically allocate memory, 32 bits or 64 bits, for some object's age, but that's not really gaining me anything in that case. If all I need is 32 bits or 64 bits, I might as well put them in the struct itself. Conceptually, the difference with an age, though, is it going to be DAVID? Is it going to be DAN? Is it going to be a much longer name? I don't know a priori how many bytes to allocate for a name. And so in that context, much more compelling to use a pointer than use some dynamic memory management so that I don't have to say all names will be 100 characters. Because if I choose all names will be 100 characters, obviously I'm going to be wasting some of those characters some of the time. And if there's some crazy name that's 101 characters, I can't support that person in my program. So pointers give us some dynamism. Yeah?
You don't have to waste time on this if it's something we should skip, but I'm a little hazy on the difference. Why would you, for enum, why wouldn't you just use an array for genders? Maybe I'm misunderstanding how you...
A good question. So enum is not giving you an array of values. It's instead declaring a whole bunch of constants. But those constants can then be data typed collectively. And it allows me quite simply then to do, one, this sort of thing, where I say that a new data field inside of a structure is going to be of this type. And then just to make this more concrete, if I scroll down to my main function, notice that I can then use this using this syntax. So we could use arrays, but I would argue it would be a messier design. I could do something like this, genders, and then I could do something like female, and then get the value of genders at that index, but it's not really gaining us anything in that case. And in fact, that's just wasting, is that helping? Yeah, let me retract that comment. It's messy. No need to do it. Yeah?
So the female that you have caps, should you be creating a new gender object and referencing female?
Good question. No. So the use of enum up here creates the constants. The use of typedef allows me to collectively treat these values, female and male, as a new data type. So I'm doing two things at once there with typedef.
Does it come up in code hinting and things of that nature?
Come up in what? Sorry?
Like code hinting?
That's a good question. Probably for IDEs that support C proper, but never, I rarely use an IDE with C, so I'm not sure.
Underlying, it's always 1, 2, 3, 4 whenever you define enum.
0, 1, 2, 3, 0 indexed. Yep, it just does it for you. So, and just to be clear, because I did it verbally a moment ago, the alternative to this, or an alternative, would be to do sharp define, which declares a constant. Then I could say female and say 0, sharp define, male gets 2. And then down here, it's yelling at me because I've done it elsewhere, or rather 1. Down here then, if I did that, and got rid of the highlighted portion, I can still use female as a constant and male as a constant, but now I have no grouping of these things as a data type, and I just wanted to introduce the notion of a gender. Yeah, Dan.
For clarity, could you do genders dot female?
Genders dot...
When you actually instantiate?
No, because no. So this is not declaring a struct called genders. This is saying that the keyword gender is a data type, and that data type can only take on the enumerated values of male or female. Good question. And if it's still a little vague, rest assured that at least so far as iOS coding goes, you don't need to be as comfortable at this moment in time with this as you would be with this. This is the type of, we'll use it, but not necessarily declare these things ourselves. All right, and one quick example on arrays. So Java, of course, has arrays, as do most languages these days. In this example here, though, let's try to tie some of these things together. So this is arrays.xcode project. Same context. We have one C file and one red file, because I haven't yet built this and installed it on a device. If I now scroll over to the right, we have some comments atop the file. Include standard I/O, just a quick sanity check. What is declared there, among other things? Printf is up there. All right, so int main argc, that looks familiar. So let's see what's going on. Prompt user for number of exams. So the context here is this is a simple little toy program that asks the user to tell me what your grades are on some tests or exams, and then it tells me my average just by adding them up and dividing by the total number of exams. So int n just gives me 32 bits or 64 bits. Printf is just telling me what to do. And this is an interesting function. We're not going to use this in iOS, but it's the quickest, dirtiest way of getting user input, even though it's vulnerable to various attacks, at least with strings. Scanf scans the keyboard in a formatted way whereby it is going to try to read a decimal digit from the user's keyboard and store it in n. But what does ampersand n mean exactly? Sorry? Address of n. So we can't just pass scanf n because we would literally get a copy of n. And scanf could change those bits, but who cares if you change a copy? You want to change the original bits. So in this sense, we need to tell the compiler, send in the address of n, whatever that is, 1, 2, 3, 4, 5 maybe, so that scanf can then take that address and then go there by dereferencing the pointer is the jargon there. So that simply reads into n a decimal digit. So what comes here? So a feature of C99, if you haven't used the 1999 or later version of C, is that you can actually declare arrays dynamically on the stack without having to use malloc and putting it on the heap. So now that I have a value for n, I can dynamically allocate an array of ints called grades of size n right there on the stack. Years ago, you couldn't just use n in this way. if you now proceed here, we've just got a simple for loop and a couple lines in it. Enter grade number something of something, plugging in I plus 1 because humans don't want to think about zero indexing. So this is a little tweak to just say, give me grade 1 of 3, 2 of 3, 3 of 3, printing out the total number of grades here. Each time I am using scanf in exactly the same way, but now I want to read these grades, these numbers into the array. So I don't just say grades bracket I, because that would just be the ith integer. I would need the address of the ith integer. So it's, again, this address of operator that's new versus something like Java. And now if I scroll down, I don't know. The example wouldn't get any more interesting to do something with the grades now, but we could average them, we could print them out. But the key takeaways here are how we use the arrays and how we read values into things by way of address. Any questions? No? All right. So now C gets a little more interesting if you want to allocate memory not on the stack, so to speak, but on the heap. And for those unfamiliar, if you think of, say, your computer's 2 gigabytes of RAM or whatever it is you have in total, the stack typically, we can think about it as the bottom. Anytime you call a function in C, or really a lot of modern languages, it gets allocated a chunk of memory on the so-called stack, and you can think of it like a cafeteria tray. If that function, let's call it foo, calls another function bar, bar's chunk of memory ends up higher up in your RAM in your computer. If bar calls baz, it ends up here, here, here. And the key takeaway here is that each of these functions return, its memory gets thrown off the stack. And the values might still be there, which has issues for security, but it's very efficient. But you keep reusing this memory. You go up, you build the stack up, you build it down, up, down. That's problematic if you want to allocate a chunk of memory that persists for the life of a program. Because otherwise, if you allocated memory in a function and it was thrown away as soon as that function returns, you could never return from functions. You'd have to just constantly call new functions just to keep things in memory. So thankfully, if this is your computer's RAM and your stack is down here, you can actually just throw stuff up here in what's called the heap so that it doesn't get reclaimed every time a function returns. So how do you put stuff up here? You use a function in C called malloc for memory allocation. And it's a super simple function in terms of usage. You just pass it an argument, which is the number of bytes that you want back. It will then execute a system call. It will say to the operating system, whether it's Mac OS, Linux, or Windows, hey, can I have 10 bytes? Hey, can I have 10 megabytes? And if so, contiguous bytes. If so, it will then return to you what? If 10 bytes or 10 megabytes are available for you. The starting address, exactly. So it will return to you 1, 2, 3, 4, 5 if that's the address of the number, the byte, the first byte in that chunk that's free. And how do you remember what the address of the last byte is? Add-on size. It's totally up to you. So it's not a Java array, which has some kind of length property. If you asked me for 10 megabytes, you better remember that you asked me for 10 megabytes because I'm only going to tell you the first address. There's going to be no programmatic way of asking me later what's the end of that address. So you have to be super careful now with going beyond the boundaries of your array. A chunk of memory is effectively an array of bytes. And here, too, is why C is both powerful and dangerous.
How does OS remember that you have that 10 megabytes?
Good question. So typically underneath the hood, the operating system will have a layer of virtual memory, even if it's only using real RAM and not actually disk. And it will have a linked list of chunks of memory that it allocates to you. And it simply has a table that remembers which of these bytes and contiguous blocks have been allocated. So in short, it keeps a free list, a linked list of chunks of memory that are free, and then another linked list of memory that's in use by someone and remembers in that fashion or using arrays. It's really entirely OS dependent, but it just remembers via some storage mechanism like an array or a linked list. All right. So, okay, that's C. Any questions? Any questions about C? Quite honestly, if the pointers are a little vague, anything at all, now is your chance. Because otherwise, I got to start assuming we all know C. OK, so here we go. Ready for a new language. Objective-C. Oh, yes. Oh, OK.
Regarding the pointers, is there an easy way to know, or just a general way to know, like which one you should be using at any given point? As opposed to like the way you do it in Java versus C, or is it just think always use a pointer?
As opposed to use a pointer as opposed to what? There are no references in C.
Okay.
If that helps
So you never
take it off the
set
table.
Like a variable, that you're never going to reference a variable then. You're always going to just reference the memory.
Oh, good question. No, so it should be more clear. You can absolutely reference variables and values. For instance, in this same program, array.xcode project, here's an int called n. So that's 32 or 64 bits. And later in the program, I can absolutely refer to that as n. For instance, I could do something like this, printf, the value of n is %d, and then I can say n. So you can absolutely refer to variables by their symbols, n in this case, without using a star, without using an ampersand. However, here I am using the address of operator for the reason that if I want to pass in a value to a function like scanf and allow scanf to change that value, I need to inform him of the address of that value so he can then go there. I need to give him a map in memory to that value.
And is there a difference between the ampersand and the star?
Yes. So ampersand is literally address of. Wherever n is, that will figure out what its address is. By contrast, if I were the guy implementing scanf, for instance, int scanf, and it's going to take a string for its format string, and then it's going to take an int. This is a bit of an oversimplification for scanf, but this will do the trick. Storage. So if I am the guy who invented C and implemented scanf, it's going to take a string, which is the format string. It's going to take, let's just say, one pointer to an integer. So how scanf is going to be implemented is essentially get value from keyboard, and then you're going to do star storage gets that value, whatever it is. So pardon the pseudocode. So star variable means go. If storage is literally a pointer, 1, 2, 3, 4, 5, star means go there. So it's the opposite of the ampersand.
Okay.
So a silly little game you can play is I could do, this is wrong. If I want to print out the value of n, this is wrong. This would print out the address of n. But I could just say go there. So that's now right. This is wrong. This is right. This is wrong. This is right. So it literally has that opposite effect. But don't do this.
So go there and get that. It's two different things.
Correct.
Okay,
And the only, I'll admit, the only headache, especially teaching this stuff for the first time to folks, is this. The star, when it's in a parameter list, has a different meaning from when it's inside the body of a function. When it's inside the body, as it is there, storage gets that value, that means go there. When it's inside a parenthesized parameter list, it means this shall be a pointer. It doesn't mean go there. If only, what's that?
In the method, you're passing the address, basically.
Correct. Yeah.
And when you're using it, you're actually, working on that address, whatever.
Correct. Correct. So this is only to say star means two different things depending on the context. Ampersand always means the same thing. Okay, good questions. Yes?
So say the same time you want to do any manipulation, you need the address.
Okay. If it depends. I do not need the address if I just want to do this, for instance. If I want to give someone else the ability, another function the ability to do the manipulation, yes, you need the address.
Okay.
Okay.
So later on, you put n equals 2 plus 2. It's going to take n right there. It's going to take that value.
Correct. That's totally fine. N equals n plus 2 or 2 plus 2. Absolutely. That's perfectly fine. The problem, again, arises when you want to delegate control of that variable to someone else. And because we have this stack system, you can't just pass in a copy of the value because then the callee, scanf in this case, would just change the copy. That stack frame gets torn down and you're still left with the original 32 bits. So you have to give it the address, a map to the address. And to be clear, Java has this same limitation. Like you can't just pass in an int to a Java method and expect it to be changed. You would have to wrap it in like an integer object or something similar. So Java doesn't really clean this up. It just makes it harder sometimes to do these kinds of mutations.
So when you pass int star storage to scanf function, right?
Mm-hmm.
What if I just use storage instead of star storage later on? What is that?
Like this? This would not compile because the compiler would realize that you're trying to assign an integer to a variable of type pointer. So it would not compile for you unless you forced it to compile. Said ignore this error. Actually, would compile with warnings by default typically, unless you've promoted warnings to errors to just prevent this.
This points to the address now?
So storage represents, So this would not compile, but the other problem is even if you forced it to compile, you'd be changing the contents of storage, not what's at the address that was pointed at by storage. You're changing the wrong bits.
So you're changing the address itself?
Which is correct, which is useless because in this context, storage is effectively a local variable. So the only way you can jump out of that and go wherever that value actually is with the dereference operator, that is the star. So wouldn't compile, would also be wrong even if you made it compile. Yeah.
Sorry, just
No.
the scanf, the D, the percent D, is the star format, I mean, are you passing a reference in scanf, or are you passing the star format in your...
Oh, this here?
Yeah.
Yeah, so I ignored this detail. So assume that this whole format string is somehow used in this pseudocode, this comment. So quote-unquote %d is a format string, and it doesn't have to be 1. You can say, give me 3 decimal digits separated by spaces. There would have to be more code that I'd write here in order to parse that string and figure out, do I want to get an int, do I want to get a char, a float, or whatnot. I've oversimplified scanf.
I just meant the header where you said int, scan, char, star format. Are you really passing that?
Yes, this is correct. So the only true part of the story, to be honest, is this here. Because yes, this is a string that I'm passing that contains 0 or more format codes. And by format code, I mean something like %d or %s. So, and again, if this looks cryptic, char star is string. So if we were writing this in Java, we would instead say something like string format, if that helps bridge the gap. And the difference here in Java is when you pass a string, it's capital S string, which means it's an object, which means it's automatically being passed by reference, which means you don't run into any of these same issues. Yeah?
In the header, did you put int storage without the star, and then in the body return storage?
Good question. Oh, and let me tweak. Let's not call these headers. Instead, signature or prototype. Header would be really the file in question. So you could return a value. If you're going to return a value, though, I would just remove this altogether, and I would instead say something like n gets the return value of scanf. So that, too, is a mechanism via which you could have one function get a value. It's not changing the value. You change the value yourself. But the corner case I'd point out here is, well, what if you want to get 2 values? Then you're kind of stuck. And so pointers also allow functions to effectively return multiple values by way of their arguments.
If you only needed one value, though, in terms of resource consumption, which one would be more efficient? So you would return a value, or is it just that easy?
They're pretty equivalent in this case. There might be some low-level compiler difference in number of cycles consumed, but you'd be passing in because a pointer is typically the same size as an int, you wouldn't be saving any space in terms of the bits being copied. So really wouldn't gain much. Coin toss, I think. Good question, though. All right, and I promise not to take for granted 100% what pointers are, because we'll still continue to see them. Other questions? All right, that was a lot. Why don't we take our 5-minute break here and then return to a brand new language? All right, so we are back. Brand new language, but let me first emphasize this. If that was too fast, or if pointers were long enough ago that a 20-minute crash course was not sufficient, realize again we have a whole bunch of C-specific examples in the C subdirectory for tonight's source code. By all means, on help.c76.net, ask questions about them, Google around for pointer tutorials, but also rest assured that in this next iOS spec for the setup thereof, we'll also provide you with some recommended readings that will help guide you through some of these new and old topics alike. So, and again, this topic will recur enough that I think it will sink in by way of example, not necessarily formal definition. So with that said, let me go ahead and open up Xcode again and open up a project called, in our Objective-C subdirectory tonight, Hello Objective-C. Just as we saw the simplest possible C program a moment ago, here is what's arguably the simplest possible Objective-C program. Thankfully, there's some familiar syntax, but there's also some new syntax. In fact, some new symbology like the @ sign. You'll actually find that as a theme of Objective-C, the @ sign was often introduced when they wanted to add some feature that needed some kind of symbol that didn't clash with existing C code. So we'll see it in a few different contexts. Some of this we'll wave our hands at for now and for tonight, but we'll come back to it. But the first thing that's different seems to be this. Anyone happen to know what the difference between sharp include and sharp import is or might be? Sadly, the very first word in the file is different, so yeah.
For import, it only gets used once.
Import only gets used once, exactly. So this is a smarter preprocessor mechanism whereby historically in C, you actually had to jump through some hoops in the .h files that you're including, declaring with sharp define, and then using if ndef, which is another preprocessor directive, to make sure that you don't accidentally copy and paste the same file to the top of two different files. The problem being, if you had declarations of data types or of structs or of anything else that's interesting in those header files, if you accidentally paste it twice, it's like writing the same function twice. The compiler will typically yell at you and just not work at all. So import just saves the world some trouble. But for the most part, you can just now start using imports henceforth. So we will not write C code for projects. We will write Objective-C code. So the previous discussion was really meant as a stepping stone to what we'll now you'll now want to absorb. So foundation.h. So this is Apple's so-called foundation class. This contains a whole bunch of stuff, some of it carried over from Steve Jobs' Next Step days. So we'll actually see many references to his old company throughout the iOS SDKs. And foundation classes has very useful low-level functionality, much like standard io.h had for printf. So we'll see some things before long. This is identical here, but in iOS apps, you're not going to be running things at the command line, and so we won't use argc or argv. @auto release pool is a feature of iOS 5 that was released last summer and essentially refers to automatic memory management. So a year ago, memory management was a lot harder than it is right now. Thankfully, they have simplified things, but we'll still talk about how things are working underneath the hood, since certainly online, in textbooks, and just in general, it's a useful thing to understand what's going on underneath the hood. NSLog henceforth will be our printf equivalent. NSLog is a proper logging function. NS refers to the Next Step days, again, Steve Jobs' old company, and this is indeed a logging function, and it's how we will be able to print to the screen for diagnostic purposes, typically. You wouldn't use this to display something on the iPhone or iPad's glass. Hello World is the same as before, but there is something else that's different here. That. Any guesses as to what that represents? So it's for strings. So in Objective-C, strings are actually promoted to first-class objects, so to speak, whereby with the @ sign, quote unquote, hello world, actually means this is now a Java-style string object that we can pass around and call methods on. But it still looks like a string, but the @ sign means this is actually an object. Then it's shorthand for actually having to allocate a string and then assign its individual characters. So this is distinct from char star. Char stars still exist, but they will much less commonly be used. So for now, assume that you'll almost always need to put an @ sign before any strings you use in Objective-C. And double quotes are necessary. And then return 0 is the same, means all is well. And just for now, and we'll tease this apart in the future, @auto release pool, this just means automatically manage the memory of anything that's going on inside of this, although that's a little bit of an oversimplification. So if I run this, let me go ahead and do that. I can hit Command R or click Run at top left. This will compile. This is actually a Mac application. It's not an iPhone application, so there's no iPhone simulator to pop up. But there is my NSLog message. I see the date and the time. I see probably the process ID or whatnot here, the name of the binary, and then finally its output. Similarly, if you connect an iPhone to Xcode with a USB cable, you can see the same diagnostic output, especially if a program has crashed and has been logging all the time. It's not uncommon for apps even in the App Store to still have NS logging messages in them, so you can actually see and even try to diagnose why some application is crashing, but typically for production code, these things should not be printing because it's just wasting space on the device printing these things out. But if you're curious as to how some of your apps are working, you can actually sniff your own phone's debugging logs if they are enabled for some application. Oh, and as an aside, I think we said this in lecture 0, but it's worth mentioning now. Because, as you'll see in the iOS setup project spec, you do not need to pay to join Apple's developer programs to start writing iOS code. If, however, you own an iPad, iPod Touch, or iPhone, and you want to install these simple little applications or your own projects on your own phones, you'll typically need to pay Apple $99 for that privilege, or $299 if you want to do it for your whole company, a whole enterprise account. Or because you're in a class, we have the ability to let you do this for free by adding you to the courses account. And all we need to know, as you'll see online, is your device's unique identifier. There's a whole cryptography system Apple has in place to really tighten things down. But the one gotcha is that you won't be able to submit to the App Store. That's probably fine, but just realize that if you plan on writing iOS apps for fun or professionally after the course, it wouldn't be bad to sign up now so that you can familiarize yourself with the paid developer program, and you can just kind of transition immediately to App Store stuff and whatnot, but realize you can postpone that decision too for several months and at least use the courses account for now. So more on that in the project specs. All right, so that's Hello World, but not all that compelling. But let's look at what's now up here by default. So I have a few new things. I've got main.m, so now my code files have changed to .m files, no more .c files. M typically denotes methods, so even though this is not yet an object-oriented program, .m refers to this is where your methods typically go. Supporting files. So this you typically get for free because Xcode has a bunch of templates. And so I just got some prefab boilerplate code. A PCH file. Anyone know what that is? So it's pre-compiled header. You'll rarely, if ever, have to touch these, but it's effectively files that can get automatically prepended to all of your own files so that you can factor out some common functionality, making sure things like foundation class code or libraries are accessible to you and so forth. But for the most part, you can close your eyes to those. Foundation.framework. So this looks like a little toolbox because it's not files per se. This is essentially an indication that you're going to link against the foundation libraries. So when the code is compiled, even though you have your header files typically like this just has the functions declarations and the methods declarations. The library will actually have the bytecode or the binary code that implements those methods. So that's just there as a visual reminder of what you've linked against. So this will be relevant. Typically not for the course's assigned projects, setup or staff choice, but for your own student choice project for iOS, if you want to use like MapKit or you want to use some the contacts library or similar, you might have to go through various menu options to add more toolboxes here so that you can actually use the map library. They're deliberately left out so that you don't bloat your binaries with libraries that you don't need by default. So just realize that that is sometimes necessary. And then this is my program, which I've run, so it now looks like this without looking like it's in red as before. All right, so Objective-C. What do we get now from this new language? So we get some new data types. So there are Boolean data types, all caps is necessary. There's an ID data type. There's nil, which is a special type. And there's a few other things, but these are the big introductions. So what is the value of a bool in Objective-C? What are the possible values? Incorrect. Incorrect. Yes or no? Okay, so it's yes in all caps or it's no in all caps. Who knows? Probably an interesting story there, but that's the way it is. And it is bool in all capital letters. So you will see literally yes and no in all caps. ID is interesting. If you did have a non-trivial background in C, you might recall void star pointers, which were both powerful and a little messy in that you could pass around anything by address. You could implement effectively collection classes for anything using void star pointers, albeit by sacrificing some type safety. ID is very similar in spirit to a void star pointer, but it's a little special in Objective-C in that even if it is null, a zero value, you can still perform operations on it without your code crashing. So this is huge. When you have a value, and that's actually a slight oversimplification for now, but an ID data type means this is some object. Don't necessarily know or care what it is, but this is a pointer to some object. However, that pointer could be null, but not really null. That's a C thing. It could be nil. So nil is Objective-C's analog of null, where they're both 0 bytes, but, and this is where the story is correct that I started telling, if you call methods on nil pointers, your program does not crash. They are simply silently ignored, which is both good in that programs crash with less frequency, but bad in that bugs can sometimes be hidden because you don't realize that you've done something wrong. But it does eliminate otherwise what would be some fairly mundane error checking code. Is this null? Is this null? And this null, which is just requisite in something like C. So we'll see this in use. But for now, these are the three biggies that we're going to start seeing all throughout some Objective-C examples. Foundation data types. So foundation, again, just refers to Apple's big library that has a lot of basic building blocks. One of them is the function nslog. Another of them is these data types, nsinteger, nspoint, nsrect, nssize, nuinteger. The only downside here is that almost always you would assume in an OO world that capital letters imply these are classes. They're not. So these are actually primitives underneath the hood. It's a little unfortunate. NSInteger, I believe, is just a type def, a keyword we saw earlier, for like an actual int, lowercase int. But it's one way of at least abstracting away these data types so that you're not using these low-level C primitives. You're using the foundation classes versions, even though underneath the hood, most of these are just synonyms for things we're already familiar with. So just beware that they're not proper objects, which means you can't pass messages to them. That would be like trying to call method on, sorry, I haven't defined message yet. You can't call methods on primitives, so you can't call methods on these things either. But there's not many. This is among the few exceptions we'll care about. All right. So we'll see those before long in action. .h file. So now's where things get interesting. So whereas in Java you would typically declare a class and define a class, that is, implement a class, all in the same .java file, in Objective-C you actually take the C++ approach, whereby you still have header files, you still have .m files instead of .cc or C++ CPP files, but you have two separate files where you put declarations in one, the sort of skeleton of things, and the implementation or definitions of things in the other file. So a .h file in Objective-C looks like this. And unfortunately, one of the things that was painful for me to wrap my mind around is that Objective-C uses different jargon for the same ideas and uses conflicting jargon for the same ideas with which you're probably already quite comfortable. So for instance, @interface in Objective-C means what in Java? Take a guess. No, it doesn't mean interface. It means class. Okay, so this is exactly the kind of stuff that's just a little annoying to get used to at first. So this means here comes a class called foo. The colon, sort of C++ style, means it descends from NSObject. NSObject is a class in the foundation library. So NS still stands for next step, but this is a proper class. And the colon is like Java's extends keyword, for instance. The curly brace here and the closed curly brace, this is where you can declare any instance variables. So in Java, you would similarly do this between the curly braces in the class declaration. So syntactically, the only thing that's really different here is how we imply inheritance and how you define a class. You use @interface instead of class. There is @class, but that does something else. But we'll see that eventually. Okay, lastly, and the thing that's syntactically a little weird, I've always thought, is that to declare your methods for this class called foo, you actually put them outside of the curly braces, but before @end. So these were the kinds of things that I personally just found frustrating at first, is that it's just not a very pretty layout. I would put more stuff inside the curly braces, frankly. But they do have this, well, it's not even symmetric. @interface, @end is not really the opposite of one or the other. But this is all it is. There's no conceptually new information here versus Java, C++, PHP, other languages. It's just different jargon and syntax. Yeah? In the header file, you would not want to, and the compiler would probably yell at you, even though that's really a convention.
So essentially, it is like interface.
Except for the, well, is it like interface? Similar in spirit, then. There are some similarities, certainly, but we'll see more sophisticated uses, and we'll also in a moment introduce something called protocol, which is a closer analog of Java interfaces. Okay, so we'll tease this apart with a concrete example in a moment, but here's the M file. It's at least a little simpler. It's @implementation, then we say the class name. We don't mention the inheritance anymore, and then inside of here we implement the actual methods. And we'll see the syntax for implementing methods momentarily, but for now, those are the canonical structures of a header file and of a methods file in Objective-C. We will see that there are visibility features. They're not as commonly used because you can actually, for instance variables, you can flag Instance variables as private or public or protected, very similar in spirit to Java, but you can't really do the same thing for methods. If you know that a method exists, even if it's not documented, you can still call it. So there isn't the same kind of visibility protection as there is in some languages. This is one of the ways, for instance, people can take advantage of undocumented iOS features to do fancy secret things because the methods are there and the objects are listening for those methods to be called. It's just Apple didn't tell the world that they actually exist. So this is really a result of the language's design. So what about class methods? How do we go about declaring class methods? So syntax here is a little different. Frankly, it's kind of nice. In Java, you have to say static. In PHP, you have to say static. In Objective-C, you just say plus. This is a class method, and a class method is the definition for which is what? What does it mean for a method to be a class method as opposed to an instance method? Exactly. You can just call it on a class via the class's name without having to instantiate, as with the new operator or the equivalent, in advance. You can just call it. And it looks like that. And alloc is one of the most commonly called class methods, whereas in Java we have the new keyword. C++ we have the new keyword. In C we have the malloc keyword. In Objective-C, alloc is the keyword with which you can allocate an object of a specific class. So it's like new in that sense. Instance methods, here's an example then of how we can allocate a student object. So let's assume for the sake of discussion, I've declared a student class somewhere in student.h or whatnot. So I have a class now called student, capital S. I can call its alloc method with this syntax here. Now this is a little weird too, and it's not as bad as Lisp if you're familiar with all of its parentheses, but there are a lot of square brackets in Objective-C. This line here is effectively equivalent in Java to a method call like student gets, this isn't quite fair here. This would be something like new student. So this is pretty much what we're doing here right now. The syntax, though, is as follows. You instead mention the class's name in square brackets, space, and then the name of the method that you want to call. And I'll start now introducing the word I accidentally used before, messages. So you don't really call a method in Objective-C per se. You instead pass a message to a class or to an object. And the name of that message is what we think about as methods, but this is just the jargon that the Objective-C folks typically latch onto. So message passing is like method calling, just a different way of viewing the world. Now instance methods are declared not with pluses but minus signs. So there's actually a nice syntactic simplicity there. So here are some sample instance methods that might exist. For instance, in a student class, I might have a getter for a student object's age, and by convention, that's just going to be called something like age. The Objective-C world does not declare instance methods like get age, get foo, get bar, get baz. Just say what you want. Don't say get, just say the name of the variable in question that you want the value of. So stylistically, too, this is deliberate. And as we will say in the setup spec, we do recommend that you adhere to Apple's coding style, simply because they're sort of the then your code will match most everyone else's out there. So like a minus sign, space, int, which is the return type, no space, and then the name of the method that you want to implement. So these are not implemented here. These are just declared. So these would be in our H file. We'll see this in action shortly. But this would be a method, presumably, that returns a student object's age. Meanwhile, this would be a method that sets a student object's age. But notice the slight syntactic difference here. When you want to pass parameters in Objective-C, we're going to use colons quite a bit, not parentheses as you might in Java. So set age is a setter. It doesn't return anything, but it does take as a single argument an integer that we will call age. This, too, is an important convention for reasons we'll soon see. When you implement getters, just call it by the name of the value you want to get. Don't say the word get. When you have a setter, make it identically named to the getter, except prefix it with the word set, and then capitalize the first letter that was in the getter. This will be important because whereas in Java it's a pain in the neck to implement getters and setters, you might have a file this long with just stupid functions that all they do is return values and set values. So in Objective-C 2.0 they introduced what's called a synthesize keyword, which can let you automatically generate all of that code for you. And automatically at compilation time, it's not like generated for you and then you see it, it's all hidden from you, which is a wonderful value add so you don't clutter your class with fairly mundane functionality. Now another type of instance method that's quite common common is this. An init method exists in most every class, even if it doesn't do much or anything at all. Typically returns void, as in this case here. And it's meant to initialize an object, and we'll see examples of this. So whereas in Java, you call the new keyword, and then you call the constructor by way of parenthesizing after the class name, in Objective-C, that's also sort of a two-part process. You call alloc, which is equivalent to new, and then you call init, which is equivalent to sort of the parentheses that imply calling an actual constructor. So we'll see this example in a moment. But you can also have constructors, but don't call them constructors. You can also have initialization methods that actually take multiple arguments. And this too is a little weird in Objective-C in that it kind of sort of has named parameters, but they're not quite. So this initWithName method apparently returns nothing, but it's not called initWithName. This method's name is initWithName and age, with colon at the end of it. So love it or hate it, the Objective-C world generally encourages the naming of methods in a way that read like short phrases or sentences, even though that is at some cost of verboseness. So this is only the beginning. Wait till you see some of them. So initWithName, then you specify what you want as the first argument. This is apparently a pointer to a string object. NSString, again, is the long form name for the @ abbreviation that we saw earlier. It's going to be called name. And age is effectively the second parameter, and it's going to be just an integer. So I say it kind of sort of has named parameters in that the method's name is really initWithName and age. But even though this kind of looks like it's the name of a parameter, well, then this is kind of the name of the parameter. But then what's the name of the method? This is where it's sort of an amalgam of named parameters and just C-style, comma-separated list of arguments. So the upside is that you actually have a reminder of what the various arguments are. There aren't just comma-separated lists, and you have to remember what the third argument is, what the sixth argument is. They actually read long form like this, but it's not as versatile as like JavaScript, where you can pass in an object or hash in any old order and just name all of the parameters. So it's sort of a in between those two extremes. All right. How do we actually call things like this? Well, we'll see some now familiar syntax. If I want to get a student's age, and at this point in the story, assume that I have a student object called student in lowercase, and I want his or her age, student age will return that age. And hopefully I have something on the left-hand side to assign it a value, but this just invokes the getter. This invokes the setter, and these two lines invoke those other two instance methods. All right, so let's actually do an example rather than look at this in the abstract. So I'm going to go ahead and open up one of tonight's examples, which is, if you'd like to play along at home in Objective-C, Students 1. Whoops, wrong click. Students 1. Well, that's weird. Let's go in here. Okay, that's a bug in Xcode 4.3.1. That's not supposed to happen either. There we go. All right. Maybe it didn't like that it was. No, not sure why that happened. Call it a bug. All right. So what is in this file before we look at the code? So this is a little sample program that I wrote that embodies the notion that uses Objective-C, that integrates the idea of making a custom class and then performing some syntactic doing some stuff with new syntax. So up top, we have main.m, which is where my main function is going to be. I've got student.h and student.m, which are going to respectively declare and define a class called student. Then I've got this precompiled header, which isn't interesting, this thing for the linker, not interesting, in the binary. So really, we have three files that are of interest right now. So let's take a look at the first, main.m, as to what this program is supposedly doing. So at the very top, we have some familiar stuff now. Import foundation.h. And as an aside, what does it mean that there's foundation/foundation.h? What does the slash denote here?
Well, foundation would be the library, and then the header file.
True. Foundation's the library, and foundation.h is the header file, but it's even more sort of low level than that. There's a directory somewhere on the file system called foundation, and in there is this header file, just for file system organization. And the compiler knows where to look because it assumes user include or something default on the system. Import student.h is also my own header file. Notice no semicolons after either of these because they're different from the C code down here. Prototype, same reason as before, but now this is Objective-C, not C. But so far I'm not seeing anything that's too worrisome other than the difference between include and import. This function prototype is the declaration here is the same. Auto release pool, I'm just going to blindly accept for today as related somehow to memory. And now let's actually do some code. So Alice here has been declared as a variable of type student star. So this is going to be the address of a student object. Well, what am I going to put at that in that pointer? What value? I want to put the address of an actual student object. So how do I get a student object? I call the class method alloc on the student class in square brackets, and what this returns to me, much like Java's new keyword, is effectively the address of that object in memory. Or it could return nil under what circumstances maybe? No more memory. Some corner case happens, but hopefully that's not going to happen with such a simple program whose first line of code is right here. So syntactically now this is very similar to C, even though we didn't see examples of the syntax yet. Alice arrow age gets 20, Alice arrow name gets at Alice, are doing what you're probably guessing they're doing. It's assigning the age instance variable to be 20 and the name instance variable to be the string object Alice. But why am I using an arrow notation here instead of dot notation like in Java or in like C structures? What does the arrow notation denote? It's dereferencing. So what's nice about the arrow here in code is that it's pretty similar to the thing I drew on the board over here and over here. My arrow was deliberate. Pointers are typically depicted with arrows somehow. So the arrow really means go to the address currently stored in Alice and then edit its age field. Now, what are age and name? They're instance variables. We'll see how to declare those in a moment, but for now know that they're just two pieces of data inside of a student object. So what about the dot notation and the star notation? It's actually not gone. What I'm really doing is this. I am saying go to the address stored in the Alice variable and then access the data member called age. So this is just like Java, the dot. This is the C discussion that we had before break. It's just that, frankly, this just looks ugly. It's a lot of characters to type. So the world introduced the arrow notation as shorthand notation for what I've written more verbosely right now. So this line is equivalent to the one that just says Alice arrow age. And if this is still a little mind-bending, realize that we're soon going to remove this syntax altogether and do things much more cleanly with just dots. We're going to hide some of these details. All right, so I'm greeting Alice. If I scroll down further, Bob's just a second example, so I can have a second student object. But this function is this program is almost identical to some of the stuff we did earlier with greeting students. Well, let's look at the greet method now. I'm not using printf. I'm instead using nslog. Notice that nslog expects an ns string, not a C-style char star, so to speak. And notice this new placeholder. We didn't have this before. We used %s for strings, and that's fine. But %s is a char star, low-level C string. %@ is an ns string. It's an actual string object. So hello, so-and-so. I see that you are something years old, and then after the end of this close quote, I should see, yep, s arrow name, s arrow age, just so I can plug in those values. All right, so let's just see this in action. In Xcode, notice that a lot of the complexity of the UI is hidden via these buttons up top right. Right now I have the left-hand view enabled, which is why I see all the files on the left-hand side of the screen. I'm going to click the middle one above the word view, and that's going to enable the debugger window, which by default is at the bottom of the screen. And that's, again, where I saw my printf output earlier. So let me go ahead and run this, and then we'll look at the student class. I hit Command-R, and that's it. Very underwhelming. This is not even an iPhone application. This is really a Mac OS command line application, even though I'm running it in the confines of Xcode. But looks like Bob and Alice were greeted in a manner we hopefully expected. So more interesting, though, is the class. So let's look at student.h and see how it jives with our story earlier. So let me zoom in. Looks like pretty consistent. I introduced the @public keyword, even though it wasn't strictly necessary here. @interface student inherits from the NS object class. So Java hides this detail. Anytime you declare a class in Java, it's automatically extending from object, capital O. In Objective-C, you have to be explicit. It's probably a little better in that you know now what it's actually descending from. Open curly brace, close curly brace. So inside of the curly braces go not my methods, but my instance variables. Both of these are public, apparently. So this is a little messy, frankly. There's no colon. You only do it once, and it applies to everything below until you change it to @private or @protected. But this gives every student object an integer called age and a pointer to an NS string called name. So pointers will still remain in Objective-C. It's not a pointer to char star. Now it's a pointer to an actual object. So it's more like a Java reference, but also still a little more dangerous in that it's an actual address in memory. So what about the M file? Well, I actually really didn't put much effort into that. That's it right now. Now we can certainly do better, but for now I just wanted a container. So really this is just a glorified struct that I've implemented thus far. So let's try to take this to the next step and do something that's a little more interesting, which we have in version 2 of the students. So in version 2 of the students, I'm actually going to introduce the very common paradigm in Java of getters and setters. So let's spoil the results by looking at the usage first here in my main.m file. So this looks the same, What's the first line of code that looks different so far? Okay, so set age. Apparently these two setters. So how do you call a method call a setter? Well, you don't really call a method. You pass a message called set age, passing in some argument, in this case 20, to an object Alice. Same deal here, set name to @Alice. So it's functionally equivalent to what we do in Java and other languages, just syntactically different. The square brackets refer to message passing. And then Alice, actually we can clean up the greet method here. For Alice, if I scroll down to the bottom, notice that my implementation of greet now looks like this. And this isn't arguably any better, frankly. This is arguably more confusing to me. But at least take away from this what's going on. So what does this mean exactly? Bracket S name bracket.
Get the value of name.
Get the value of name, but be more technically precise. Pass a message called name to S, which is effectively equivalent, higher level, to call the getter for name. So that's actually a method call now. Yeah?
That assumes you created a getter, or does it default give you a getter called whatever that variable is?
Good question. At the moment, it's assumed I've created it. But we'll see the student class in just a moment. So for now, that appears to be something I've implemented. But even that we can hide away. So we'll generate that code automatically before long. So there's arguably a downside here. Now I'm effectively doing a message pass, which has some overhead in terms of calling a function and so forth, and maybe a stack frame is built up and so forth. So this is actually a step backwards from actually just accessing the instance variable directly with the arrow notation. But on scale, certainly when we're doing more interesting things, going through method calls is actually a good thing typically. And frankly, now that we all have gigahertz devices in our pocket, these sort of low-level optimizations is not where you should be spending your time. Much better if you can protect yourself with message passing as opposed to low-level bitwise manipulation of values. So in short, you will see this theme in a lot of iOS where, you could shave some cycles off here, shave some cycles off here. It's probably not the best habit to get into. Let the compiler worry about things more these days. Let the CPU take care of these optimizations for you. All right, so let's look at our student class. So in student.h, little different now. So now I decided, you know what, the world kind of likes to use underscores, be prefixed to any instance variable that's effectively private. Now these aren't really private per se, but it's again an iOS convention. Typically, if you want to be able to easily distinguish an instance variable from, say, a method, a message name, well, you would prefix the instance variables with underscores. Beware ever using double underscores, which is typically reserved for compiler usage, but single underscores are generally fine for you to use. But now it's different. So curly brace, close curly brace. Now here comes some method declarations. And indeed, here are the methods that I've promised to implement in my M file. A getter for age, a getter for setter for age, a getter for name, a setter for name. And I just arbitrarily sorted them in this way. You can organize things however you want, all of the getters, all of the setters, but this is fairly readable as is. So let's now look at the implementations of these things. I could just copy now and paste these into the new file, eliminate the semicolon, and add curly braces, but that's effectively what I've done. So let's go over to the M file, student.m. So now it's more interesting. Underneath @implementation, I have some implementations. And this is sort of the Java style, very tedious implementations of getters and setters. Return the age instance variable. Set the age instance variable. Here, though, too, kind of necessary here if you want to be able to distinguish the instance variable from the arguments. You cannot do something like this .age to avoid the ambiguity in Objective-C here. So this is a useful trick here. Return name and set name is going to be pretty much the same, whereby, oh, interesting. Why is set name suddenly different from set age?
Oh, you're copying the value?
Yeah, I'm definitely copying it. So I'm passing the copy message to name. I don't know where copy came from, but I'll worry about that later. But I didn't do that here for set age. Why?
Age is a primitive and name is a string.
Exactly. So age is a primitive, which means it's just 32 or 64 bits, which means when you copy it, you're literally going to get a copy of those bits. That's problematic, though, for pointers, because if name is really a pointer underneath the hood, and I copy those 64 bits in iOS and in macOS, well, I'm going to get a copy of what? The address, which means I'm going to have a copy of an address that's still elsewhere, but what if someone else, some other code that I or someone else wrote, changes that name elsewhere in memory? I'm going to have a pointer to that chunk of memory, but now David's name has changed to Dan, even though I did not change the name from David to Dan. So conceptually, if you want an object to truly have its own copy of something, and that something's a string, you need to implement a bit more functionality to actually copy the bits that compose that string, not just the address. Thankfully, this is easy, because a string, in this case, is an NS string, not a C string, not a low-level char star. It's an object, which means we can pass it messages. Thankfully, someone had the foresight to have to implement a copy method inside of the NSString class. So when I call name copy, this does a character for character copy. It allocates a new chunk of memory and returns to me the address of what? That new chunk of memory after copying in DAVID or whatever the name actually was, and maybe some sentinel value so it knows where the end is, if that's how it actually implements them. So necessary here, not necessary here. And the rule of thumb is generally if it's a pointer you're copying, you better think hard about how you're going to copy that value, so to speak.
Even in Java, we never copy. We just pass around the variables and the methods change, and it's just,
Maybe not in the intended behavior. So there are ways to truly copy Java strings. So this is a takeaway that transcends Objective-C itself, certainly. Maybe that's fine if you just want a literal copy of the address, but generally that's probably not the intended behavior when copying something like a string. All right, so we can clean, this is a little tedious, and man, I mean, these aren't even that interesting. Imagine if I actually had 10 fields associated with a student. Things do start to devolve back into a lot of copy and paste and renaming. So let's take a step towards something a little cleaner. So Objective-C 2.0 introduced something called properties, and we're at 2.0 now, but just FYI, a lot of resources online might not discuss some of the features we're discussing. So again, stick with the recommended books or Apple's own documentation. So notice what I've done here in version 3 of my student code. I've gotten rid of the explicit mention of age and set age. I seem to be back at dot notation, which is kind of nice. That's where we started in Java, and then we kind of ripped it away. We had the arrow notation, or the star and then the dot, or then the square brackets, but we've come full circle now to the dot notation. This is just syntactic sugar, which means this just makes people like us happy to have that same syntax, even though what's going on underneath the hood is not accessing a data field called age inside of an Alice object. Rather, this is calling the method called age on the Alice object. Sorry, that's the wrong story. This means call a method called setAge with an argument of 20 on this Alice object. So this line of code is functionally the same as, at the end of the day, even though there's some high-level distinctions, this is the same as Alice age gets 20. This is the same as Alice set age 20. But of these, I'd probably pick this one, just because it's the cleanest. Now, to get this functionality, though, you need to do a little bit of work up front. So the file here, main.m, is mostly unchanged except for this new dot notation, which I'm happily taking advantage of now. So let me look at the H file for the student class. This is where the first difference is happening. Notice now, and it's a whole bunch of syntax, but functionally quite compelling. Top part is the same. Haven't made any changes here. Bottom part is the same, so there's only 2 new lines here. So at property means here comes a property. Let's ignore the parenthesized list for just a moment. And what this line is really saying is this class called student will have what we'll call a property that is of type int, and its name is age. Same deal here. Another property called name, and it's a string, NS string star. What is a property useful for? 2 primary things. One, it enables you to use the dot notation we just saw. So it's not sufficient to declare it as an instance variable. You must declare it as a property if you want to be able to use the dot notation. There's another feature we'll come back to, and it boils down to automatic generation of getters and setters, which is hugely compelling. Now, what about all these things in parentheses? We'll come back to this, but let's plug them off in reverse order. Read-write just means that this property should be readable and writable. What does that really mean? It means that there's a getter and there will be a setter. Read-write. If you said read-only, there would only be a getter, no setter, which you sometimes want to hide your data or encapsulate your data all the more tightly. Non-atomic just means this is the simplest of apps. There's no multi-threading code here. I don't need the overhead involved of writing atomic thread-safe operations. Don't automatically generate any such code for myself. It's non-atomic. Just saves me some CPU cycles. Typically for the class, that is what we'll want to use, non-atomic. Lastly, assign and copy have to do with memory management. So I'm going to wave my hands at that for now, but I'm going to say for today's purposes, assign is typically used for primitives, and copy, or a new keyword called strong or weak, is used for pointers. But more on that to come. So for now, this is a property keyword that enables the dot syntax, but it's also going to enable something else for us momentarily. First, let's go into the M file just to see what, if anything, here is different. And in fact, none of this is different. So the only change is the enabling of dot notation by declaring those things as properties. But let's take this the full 9 yards. Let me go ahead now and open up version 4, where we have another refinement. This time in version 4, we have synthesized properties. Well, what do I mean by that? Well, my M file now is identical. There's no change in my main function in this story. In my header file, I similarly have those properties, but guess what? I've started throwing away code that frankly is pretty copy and paste in any type of program. What did I first apparently eliminate? All those methods that were at the bottom and all those instance variables. So it seems like I've thrown out the window a huge amount of functionality and the ability to store any information related to student, but no, we're going to get a lot of that functionality back for free. What I've retained is only these 2 lines mentioning properties. But that's it. If I scroll down, there's nothing more in this file. That's it. So that's starting to get pretty interesting. And I frankly don't even need these curly braces. If you have no instance variables, you can simply say that as well, for better or for worse. So M file, this is now a little different. In my M file, where previously I had all those getters and setters, 2 getters, 2 setters, they're gone too. But what's new, apparently, is these 2 lines. So what are these 2 lines doing for me? This one here is synthesizing, that is automatically generating a getter and a setter for age, and it's going to back that property called age with an instance variable called _age. In other words, this one line will not only give me back the instance variable that I deleted, so I don't have to bother writing it myself, it will also generate a getter and a setter. Why a getter and a setter? Because in that comma-separated list in parentheses in the H file, I mentioned what keyword? Read-write. If I said read-only, I'd only get a getter. There would be no setter, and it would be an error, or just it would be silently ignored if I tried to set this age value. Same deal with name. It, too, is going to create my getter and setter. It's going to dynamically create for me an instance variable of the appropriate type based on the header file called _name. And this is just an Apple convention, too. It is also correct just to say this, but in this case, the instance variables would be called age and name, respectively, and that's fine. But then if you really want to do some low-level operations whereby you actually access the instance variable because you don't want to go through the functional overhead of a method call, well, it's a little less clear then that you're accessing a data member without the underscore. So again, these are just conventions. These are not functional requirements. So this is super common in Apple's code these days, and should be in yours probably for best practices. So getting pretty neat, right? We have the same exact functionality, and now I'm starting to write a lot less code. And this is, frankly, one of the things I definitely appreciate over Java, given that Java really popularized the getters and setters. What about some more fine-grained control? It's great if you can generate code automatically, but it's kind of a downside if you actually want to implement your own setter. It would be a shame to give that up, but you don't have to. So in this file, version 5, we have same implementation of main, but in my H file, I have same as before, 2 properties, no instance variables or methods explicitly defined. But in my M file, I realized, you know what, I don't really want that default behavior for the name setter. I want to do something kind of silly, frankly, but it seemed funny at the time. Anytime you try to set the name of a student to David, it's going to override that behavior. It's not going to give you a copy of DAVID. It's going to rename me to dummy, apparently. So how is this working? So besides the silliness of this, we can actually see some very common syntax. So one, how do you compare strings? Well, you can't just compare them with equals equals, because you're going to be comparing what in that case? The addresses of two strings, and that's not what you want. You want true byte for byte comparison. So how do I do this? Well, open bracket, close bracket. Here comes a message pass. Name is the name of the object that was passed in. It's an NS string. Is equal to string, does what the word says, has to have this @ sign here because I have to compare two NS string objects, but it's going to compare their values for me. If that returns a Boolean yes, Y-E-S, then I'm going to go ahead and set the instance variable name equal to the return value of this expression. What is this? Give me a new string. I don't know how big it is. So the nice thing about Objective-C strings is that they're dynamically resized, which is good and bad performance-wise. Here's effectively the constructor call, the initialization, init with string at dummy. So here too, this is why I need to know what the instance variable is actually called, even if it was automatically synthesized, if I want to control it in my setters or even my getters. Else, go ahead and just make a true copy of it in the old-fashioned way.
Could you use the setter as well instead of the underscore?
Use the, say again, sorry?
Use the setter instead of directly accessing it?
Not in this case. You would have infinite recursion because you're inside the setter. But a good, yeah, exactly. So in general, yes, but not in the setter. So corner case. What if an adversary or a buggy developer passes in nil for the name? What's going to happen here? It won't be equal to David, so we can just ignore this problem here, but I feel like a lot of my C code would crash if I did anything with otherwise a 0 address, which nil effectively is. Yeah?
We'll just ignore your...
Exactly. So here, exactly, not here. So here is the value of nil. It is totally fine if wrong sometimes logically to pass a message to nil. It will not induce a crash. It will just get ignored, and what will come back is in this case, false in the Boolean expression, or no. Here, I'm again passing a message copy to name, but that's fine because what's it going to return? Nil. Well, what was the name that was passed in? Nil, so that's great. I'm effectively getting a copy of what was passed in. So it just works in this case. Why is this useful? So on the one, I don't have to check the value of name everywhere. I don't, again, have to check, is this nil? Is this nil? Is this nil? Can silently ignore. But again, it's also easier to not notice bugs in your code simply because they're being silently ignored in this way. So some degree of error checking we'll see is called for in certain methods in particular. So in version 6 here, I want to clean up my main method and stop initializing these objects piece by piece, right? One of the upsides of explicit constructors in Java and other languages is I can initialize the contents all in one single function call or method call. So I want to clean this up as follows. When I declare Alice like this, I'm going to go ahead and say, give me a pointer to a student object called Alice, but go ahead and allocate Alice, allocate a student object, then initialize it, not just by calling some generic init method. Let me pass in an argument. So here's this init with name message, and give it a name. Oh, and let's also give it an age. So we saw this very early on in the keynote slide that had these fairly long names. We'll see longer. But this is one way of not only allocating an object, but also initializing it at the same time. This too is a convention. Typically, the default initializer, aka constructor, for an object in Objective-C is called init. All lowercase. Doesn't have to be, should be. If you want to have more explicit constructors, and again, don't call them constructors, initializers, init something, 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 start it with init in lowercase, and then proceed with often with this and this and this so that it sort of reads like a sentence. So again, conventions that are worth typically adhering to, even though we'll see some extremes. Then I call greet as usual, so let's see what's different in the H file. Nothing seems different in the H file except this. Init with name, I'm explicitly declaring, but I stole this from the slide from earlier. But notice what I'm not declaring is alloc, for instance. Like, why am I apparently safe in not declaring methods that I'm nonetheless calling later on, like alloc? They're inherited, exactly. Because this thing descends from NSObject, it's NSObject, whoever implemented that has declared these for me. So I can override them if I really want, though overriding alloc's probably not a good idea. But I don't have to redeclare them and clutter my code as such. And in the M file, notice that here is a very common paradigm now for init methods. And moving forward for any projects, do look back even at this simple example at how to structure your own init methods. Here's a default one. I just arbitrarily decided that, if someone creates a student object and doesn't initialize it, I'm going to give it a default value of John and 404, an allusion to John Harvard. I actually wasted the 2 minutes doing the math as to his age and Googling around. What he would be today. Init with name, though, we can reuse this, but here's the common paradigm. So one, in my init method, self is like this in Java, and the compiler will warn you if you don't update the value of self in Xcode 4.3.1 now. So this would be the common paradigm. If you want to initialize yourself with an explicit initializer, that's fine. Update self and then return self. And then here with the init with name and age, notice that I'm also calling the parent class. I don't know what NSObject's init method does, but I should trust that it might need to do something. So I'm going to call it first, then I'm going to update age and name, then I'm going to go ahead and return self. And here too is a design decision. This is a little inefficient. Why? Doing these two things here. If you really want to be like anal and nitpicky, why are these 2 lines of code as written a little inefficient?
You're going to that, you're going to an extra step.
Exactly. I'm going through an extra step of passing a message, aka calling a method, just to set something so simple. Like, can't I just do it directly with the instance variable? You can, but again, on modern hardware where you might actually have some error checking involved whereby you don't allow ages of certain values, you don't allow bogus names, you know what, just stand on your own shoulders and go ahead and call the code you already wrote and don't try redundantly implementing it here. Certainly not when we're implementing UI mechanisms where the bottleneck is going to be the human, not your own code. Yeah?
I was going to ask, is there a way to switch on nil checking for testing?
Nil checking.
The compiler or...
Oh, good question. Not to my knowledge. Is there a way to turn on sort of conditional nil checking unless you did some preprocessor trick where you have a constant that if you embrace the code with code that's just thrown away afterward. More trouble than it's worth probably in Objective-C. Yeah. Oh, ID. Okay, so ID is also a good question. Is also a convention. So ID is very similar in spirit to void star, whereby it returns a pointer to some object. ID, though, means that it can also be nil in this case, and this is just convention. Even though we know the initialization function methods for this class are going to return student pointers, the convention is to return ID so that, again, they can return nil as well. So ID is what you should always do for these initialization routines. And we can do this, we can clean this up ever so slightly more. Let me go ahead and open up version 7 here, which is our last of the students. And I'll tease you with some other features we'll soon start leveraging quite a bit, is now we can actually start doing something with this data. So this is a demonstration of an array that's actually mutable. So let's see some collection containers here, or some collection classes here. So NS mutable array is a class in Apple's Foundation library that gives you an array whose contents are changeable. So there's also NS array, which is immutable. For an NS array, you better know at the start when you allocate it, what you want to put in it and how many things. Mutable, you can add to, subtract to, and so forth. Why have 2 such different classes? What's the value of having an immutable array called NS array? Okay, so having a mutable array's advantage is obviously that it dynamically resizes. So then why bother having an immutable array that it's more efficient? In theory, then the compiler and really the author of the NS array class can probably make certain assumptions, certainly as to the size of the array, and can maybe then access things more randomly if need be, and doesn't have to do any kind of memory management, so you can throw away a lot of code. So now the burden is on us to decide what kind of array do we want. In this case, I went with mutable so I can iteratively add stuff to it without knowing in advance. So up here we have NS mutable array star students. So this means give me a variable that's a pointer to an object of type NS mutable array. On the right-hand side, I have to allocate it and then initialize it. And I don't know, to be honest, I know what this does. This allocates the memory. I don't really know what the init method does, but again, common paradigm in iOS. Almost always should you call alloc followed by array, but we'll see next week some exceptions to that. But this is sort of the convention the habit to get into, certainly. How about Alice? How do we add things to this array? Well, students is the name of the object now. I'm going to go ahead and call a method or pass a message called addObject. What do I want to add? Well, I want to allocate a student in this case. I want to initialize it with a name and an age. So I just copied and pasted the code that's trailing off the board here from before. And I could have put it on its own line. I could have declared an Alice pointer and a Bob pointer as I did previously. But I just wanted one clean line here. Same thing for Bob here. And now we have an example of what Objective-C calls fast enumeration. So Java 1.5 or 1.6 introduced similar syntax whereby you can iterate very easily syntactically over elements. This is going to assign on each iteration the variable s to each student progressively in this list. It's just going to iterate twice in this case, but we're going to call greet on each of those students. Well, what, if anything, is different over here in the student class? Well, in student.h, this is actually all the same as before. Student.m, this is all the same as before. So the value add here is now we're actually doing something that's more interesting with these objects. And we can now store things in these containers. Any question on those?
You can pass any object to the mutable.
Pass any, say that again?
To that mutable array?
Yes, any NS object, correct. So they are generic containers. You don't have to know C++ style or Java style what they are in advance. The data.
Is it a difference from the regular array or array you define?
No, even an NS array that's immutable, you can put arbitrary objects inside of it, even if they are not the same type or not even descending from the same type besides NS object. Couldn't put primitives, though, in the list. Yeah?
With this, you have student init with name, then their name, then and age, and their age. If you just wanted to create an initializer that only assigns an age and then maybe a default name, would you call it init and age, init with age?
Init with age.
Name?
So if you only wanted to pass in an age, I would call it init with age. And then you would just, like I did with John Harvard, just hard code some default value for name. Correct. Or you could simply pass in, you could expect the caller to just pass in nil here, and then you check if I'm not given a name, well, I'll assume you want John Harvard instead. So that would be another approach, but a reasonable design decision either way. Yeah?
Is this syntax based on some other language or they came up with this weird thing on their own?
No, it is. I don't want to misspeak. Smalltalk, maybe, is the original origin, but I'm not savvy in Smalltalk, so I'm just trying to remember my own history. Yeah, it was. Am I correct, incorrect? Anyone know?
It comes from Next Step. That kind of
Well, Next Step for sure, but it itself, I think, was inspired by some dialect of that, or I'll have to reread up on the history myself. Is that right? Smalltalk? Okay. Yeah.
Are there wrapper classes like in Java for like for the primitives? So like you said that you couldn't add an int to that NS object array.
Correct.
Integer.
That's a good question. Wrapper classes for
NS integer and it does float and NS. There's a bunch of.
But those are just type defs, though, right? So are there proper classes that wrap those as well?
No, but the NS integer wraps, so you can put an integer into an array.
I thought NS number was actually a proper wrapper class.
That's correct. That's correct. Yeah, it's NS number is the proper class, but NS integer, NSU integer, I believe, are just type defs, preprocessor directives that map one to the other. So yes, in that case, number could be the parent class that you perform arithmetic operations on collectively. All right, so just a quick tour through some other features and also some jargon as you start to read through things and start to see this. And then we'll end with a sense of where we're going. So piece of jargon here. So these things I've been calling messages, you can also refer to as selectors. And we'll see this again, and we'll actually see a new keyword called SEL, which denotes selector. But just realize for now, a bit of an oversimplification, that a selector is just a method's name or a message's name. So you'll see that in some reading. With regard to these properties, we saw assign, we saw copy. I mentioned strong and weak, but we'll come back to memory management in the weeks to follow. Atomic and non-atomic, we saw the latter of those, and we saw read-write. We saw how synthesize works, but in terms of collection classes, realize we only played with NS mutable array, but we're going to have some super useful ones in NS dictionary, NS mutable dictionary, which is effectively like a hash map or an associative array, hash table, call it whatever you'd like. Those are quite commonly used in the iOS world. NS set and mutable set, a set being in the mathematical sense where you don't have duplicates of things inside of them. We saw some fast enumeration, but what we didn't see yet are things like categories. You'll actually see these in some of the templates that come with Xcode these days when you get some prefabbed code. Just know for now that a category is a way of adding additional functionality to an existing class without descending from it. So you don't necessarily create a hierarchy. This is more similar in spirit to the prototype approach that JavaScript takes, where you can add functionality to the date class or to the string class by modifying date.prototype or string.prototype, if you're familiar with that. So we'll see this as a way of having what are called class extensions, or even the illusion of private methods. Protocols, we haven't seen yet, but we will see. Protocols and angled brackets are Objective-C's analog of interfaces in Java, where you can make a commitment to implementing some methods that have been prescribed in that protocol. And then in terms of error handling, we haven't seen all that much yet, other than if Boolean checks, but know that Objective-C does have exceptions, and they syntactically look like this, and they're actually pretty familiar looking from, say, Java or other languages. So just an FYI that those do exist. But there's also C-style error handling like this. This is a very common convention whereby if a method might need to return an error, exception handling has some overhead associated with it. It can certainly break the flow of the program. And just syntactically, it's a little heavy. In this case, you can pass in an NSError object by reference here, and that pointer will be populated with an NSError object, an actual NSError object that will be allocated for you that contains information like what went wrong, what was the error code, what's the error message, and the like. So again, just a teaser as to what you might see in documentation. But ultimately, we're going to have another MVC paradigm in iOS, whereby we're going to have controllers, aka view controllers. We're going to have model classes that typically you would write, and then views, which you'll sometimes write in code, but more often, at least initially, construct via a drag and drop interface that you'll probably find much more mature than what you've seen in the Android world thus far. So where we're going next week is going to be diving headfirst into this. We'll assume that we now know C, we know Objective-C, though no worries if that actually takes some time to sink in. But for the first iOS setup project, which is due a couple weeks from now, but the spec is already online, it will walk you through the process of downloading Xcode and all of the tools that you actually need. It will have you write the simplest of Hello World applications just to get your hands dirty and orient you. And then the next staff's choice will be released shortly thereafter. So I'll stick around for any questions. JP has section coming up next. Otherwise, we will see you next week. And help yourself to the candy on the way out.